So as we know, different materials have different propensities to absorb and transmit electrons. For this oxidation-reduction reaction, I have divided into two half reactions. And the point of this is that a long time ago, a situation occurred where when trying to compare these cell potentials, they were finding it difficult because there wasn't a clear floor to it or a clear place to start. It's like if somebody just showed up into outer space and someone asked them where they were. Unless they had they would just say, I don't know. Where is here compared to what, basically? And that is the idea of the standard reduction potentials. If I'm outer space, what I'm going to ask, or I'm going to say where I am, is compared to something, like compared to the planet Earth. So basically what they did was they said that the standard reduction potential of this, hydrogen absorbing two electrons and turning into gas, is equal to 0. Because when we have a voltage here, something like this, 0.76, but if one is trying to make a comparison, it's difficult to other things. Is this perhaps just a really great at pulling electrons to it, or maybe this has a very high propensity to get rid of electrons? What's going on here is it could be that one is highly resistant and the other one is not so resistant, or they're both very strong, or one is very weak and one is strong. So they needed a way to compare these cell potentials, and that is the whole idea. It's very similar to enthalpies, where they just assigned elements 0, because it's difficult to say where the floor is. Everything has some kind of potential to transmit electrons. There's no beginning. It's similar to the example where I said the universe. There is no clear beginning or end to it, at least from our perspective here. So there's no obvious. It's not like a 100-meter dash or something like that. There's a starting line and a finish line. Here, there's no starting or finish line. There's just different levels of some place. So by assigning hydrogen 0, we can now solve for all the remaining electrical potentials. So the electrical potential of the cell, so to give an idea of how this works, the electrical potential of the cell of this example will be the sum of all of the electrical potentials of what's going on in here. So it'll be sum of this half reaction and this half reaction. This, as said, is equal to 0. So that means that this is equal to 0.7 volts. And to give an idea how this continues, I have another example here where now that I know this standard reduction potential, to show how it's used to get a comparison, now I've got a different oxidation reduction reaction. Zinc, but this time reacting with copper, forming solid copper and zinc ions. This is an illustration of what's going on. There's solid zinc. The electrons are traveling this way. And this is what's going on at the solid over here, and this over here. As the electrons leave, these zincs go from solid to becoming an ion. So it leaves, and then as the electrons travel over here, these copper ions are attracted to the cathode over here, and then they join to become a part of this solid. So this solid gradually will dissolve away, and this one will get larger and larger. But anyways, this is more about the standard reduction potentials. So I have this oxidation reduction reaction. I want to know what the cell potential is. And this just means standard conditions, just like everything else. So what this will be is the sum of this reduction potential plus the other reduction potential. And the electromotive force, the current is the electromotive force, 1.1. 0.1 volts. And I know what this one is from the last comparison, from the last experiment. So this one was 7.76. So now I can figure out what this is. Obviously, this is and that's how they came up with the standard reduction potentials. So there's a huge table, it's got them all listed. They're written from a reduction point of view. So this over here, this is being oxidized, it's not being reduced. So what I would do is just flip this around the other way and it would become a minus sign. So if I looked this up in a table somewhere, it would show up like this. And it would be equal to minus 0.76 volts. It's the same thing, it's just the opposite way. So whenever I'm doing problems with these things, they're all going to be listed in this reduction point of view. But obviously, in an oxidation reduction reaction, one is being oxidized, the other is being reduced. The one that is oxidized, losing electrons, I just flip it around and I flip the sign. So like this one. Here, it's just turned around, and then this is positive instead of negative.